Back everyone. Now, this time I'm going to provide you with a full course of further mathematics 9231. Right? So stay tuned. Let's get started. All right, welcome back. Now, before we get started with our rational functions, I would like to bring you back to what you have learned in A-level mathematics. Right? Now, types of functions. Mainly, we are focusing on two types of mathematical functions in this case. Generally, we have algebraic functions, and then some of the examples of algebraic functions are, I think most of you knew this very well, polynomials. We can have rational functions, and then lastly is piecewise. Of course, our focus in today's topic would be rational functions. Now, other than algebraic functions, we also have another category of functions which is known as transcendental functions. Right. And then under transcendental functions, we have exponentials and logarithmic. You have seen trigonometric functions before, and then some of you may have heard of some of the spatial functions before, like gamma, W functions, and so on and so forth. Now, our focus today is, I would like to stress again, is rational functions. All right, our topic is rational function. Our learning objective for this topic are number one, A, we are going to sketch graphs of different types of rational functions, and then including the determination of oblique asymptotes in cases where the degree of numerator and the denominator are at most 2. Right, now there's the first one. Our second objective is to understand and use the relationship between graphs of y equal to fx or y squared equal to fx and so on and so forth. Right? Um, Section B is all about transformations. Right? We're going to start off by looking at the motivations behind the use of graph. We're going to look at section 1 of the usage of the graph. Here I'm going to bring you to one very simple example to get you started with how to sketch a graph. Now we're going to look at if the volume inside um, of a bicycle pump is given as x, which is represented as 8.2 cubic inches, and then the pressure is given by y, which is given as 19.1 pounds per square inches. By using the Boyle's law, we can write this relationship between the pressure and the volume itself, which is given as y equal to 157 over x here. All right, now before we get started with sketching the graph, there are a few guidelines that we are going to follow whenever we are going to sketch any sorts of rational functions or any types of graph to be general, right? Okay, guidelines for sketching graphs here. Now, I did not actually put in all the necessary guidelines. I have already highlighted the main guidelines that would give you the main features of the graph required in your exam. All right. Of course, in the future, if you want to explore more, in particular, the section of the graph itself, you might want to include some other extra guidelines, but these guidelines will be sufficient for your exam purpose. All right. So the first guideline would be we have to identify or determine the domain and range of functions where necessary. All right. Now, usually domain is given, and then range usually are not given. So we might want to either sketch the graph and then determine the range from the graph that you have sketched, or by using calculus, or by using discrimination. So these are a few methods that we use to determine the range of function here. Right? Now the second guideline, we should always identify the x and y axis intercept, or identify and determine the intercepts of the x and y axis. Right. All right. Thirdly, we have to identify or determine the asymptotes. There are three types of asymptotes of our interest here. They are vertical asymptote, horizontal asymptotes, and the oblique asymptotes. Now, next, we also need to identify and determine any stationary point or points in this case. The three types of stationary points that we are interested in are the local minimum, local maximum, and then of course we have the inflection. Right. Now, this is the guidelines that we're going to use to sketch the first graph, y equal to 157 over x here. Right. Now, please stay tuned. I'm going to show you how we're going to apply these guidelines to sketch our first graph. All right, we are ready to sketch the graph now. Okay, now just to recall the guideline, the first one would be we are going to identify the domain if we can. Right. Now, just to recap again, the the variable x actually represent the volume of the gas, whereby the y actually represent the pressure of the gas found inside the bicycle pump. Right. So just to rewrite again, in this case we have x is the volume, and then whereby y is the pressure itself. All right. Okay. Right. Now you might want to ask yourself like, is there any domain that we are supposed to specify here? Right. Now, to show you how to sketch the graph in general, I'm going to use this domain here. I would say that um, x are all real numbers, All right. Now, such that um, x cannot be equal to 0, right? So it can be any real numbers except I would say except x equal to 0, right? So this will be the domain for our volume itself, or for this function, all right? So I hope that's clear. That's the first guideline. And then now, typically when we mention real numbers here, we are actually looking at volume can be negative. You can have negative volume. Can you imagine that? All right. For me, I can't imagine negative volume, right? Now, later on, we're going to revisit these domain sections where we're going to link this domain back to reality. At this point of time, we are just going to focus on the mathematics itself. So that's the reason why we assume we are going to take all the real values for our volume here. Right? So this is our first assumption, just for the purpose of sketching graph. Right? Now, secondly, we are going to determine any sort of x and y intercepts. X and y intercept. All right. Now, because we know that x cannot be equal to 0, therefore we cannot have, therefore no x or y intercepts in this case. Okay, that is easy. Right. So we have visited the second rules or the second guidelines on how to sketch this rational functions graph. Right. Okay. Now the third one. Now the third one would be we will have um, to identify any asymptotes. Okay, we have to identify any asymptotes. So the first asymptotes that we can find very easily is given here. Since the x cannot be equal to 0, therefore x equal to 0 is the vertical asymptote. Is the vertical asymptote here. Okay, and then there you have it. There's the first vertical asymptote. Now, the tips on accessing the vertical asymptote is to observe your denominator. So, by equating your denominator equal to 0, that would actually give you the equation for all the vertical asymptotes. Right. In this case, we only have one factor at the denominator. Therefore, we only expect to have one vertical asymptote. If you do have two factors or more than that, then you have multiple vertical asymptote. Okay, we are sort of done at this point. Okay, then secondly, how do we determine if we have any horizontal asymptotes? Now, the simple rules to follow for horizontal asymptotes will be here. We are going to as the x value approaches positive or negative infinity, which means we are actually studying the end behavior of the function itself. So what will happen to the value of y or the function y in this case? Now, from here we notice that as the x approaching positive or negative infinity, the y itself would approach, you would guess it, right? As this number getting larger and larger, the y will approach positive 0. Sorry, the y will approach 0 in this case, right? So as the x approaches positive or negative infinity, the y will approach 0. So therefore, we're going to write that down as y equals 0 is the horizontal asymptote. All right, so I hope that is clear. And then, of course, lastly, you might be wondering if there is any stationary points. So we can try out guideline number 4. All right. To find the stationary points, we are going to perform differentiation here. Now, if we get the first derivative, our answer is actually 157 x squared. We notice that x cannot be equal to 0 in this case. And then our uh, first derivative cannot be 0. All right, except I would say uh, as x approaches infinity. But then again, we won't be able to tell which infinity value would actually give us dy dx equals 0 in this case. Therefore, we will say that in this case, we don't have any stationary points. So no stationary point. No stationary points here because we can't actually pinpoint exactly where is that stationary points located. Right. So therefore, there is it's not a necessity to go through the second derivative to figure out the nature of this stationary point. Right. And now at this point, we are ready to sketch. Okay, we have all the informations we need now. Firstly, we have the vertical asymptote, which is x equals 0. We have the y equals 0 as the horizontal asymptotes. So therefore, the horizontal asymptote is basically y equals 0, which is this line here. So all the asymptotes, we are going to use broken lines just to signify that the graph should not be passing through this section at all. Oh yeah, I forgot. Let me label this as x and y. Okay. Now we also have x equals 0 as the vertical asymptote. So I'm going to label this as vertical asymptote. All right, and then there you have it. That's our vertical asymptote and our horizontal asymptotes here. Now, do we have any x or y intercept? We don't have any in this case, right? Now, therefore, the graph in this case um, for the approximation to the sketch itself, right? Once you have identified your asymptotes, generally the asymptotes has sort of give us four partitions here. Therefore, the graph will only exist in those partition. In this partition, this one, and this one here. Right. Okay. Now, which partitions will the graph exist then, right? And then how does it look like, right? Now, because y equals 0 is the asymptote, x equals 0 is also the asymptote, which means the graph will be approaching this direction, or it could be approaching from this direction here, because it's getting closer and closer to the asymptote. And then as for the vertical asymptote, it could be approaching this way, or it could be approaching this way. The same go for this section. The same go for this section. Okay, now you can see that there are like eight possibility here, right? But we're going to narrow down that possibility so that we can draw the graph easily in this case, right? Now, first of all, for any x that is greater than 0, for any value of real value of x that is greater than 0, for sure the pressure will be greater than 0 there, right? So we know that for x, I'll write down here for, okay, let me clean this up. Okay, let me write it down here. For any x value, right? For any x value, I'm going to write it down here. For any x value that is greater than 0, for sure the y will be greater than 0 here. Therefore, we know that for this partition here, the graph can only exist in this section. For any positive x value, we will get a positive y value. So therefore, the graph would actually exist this section. Therefore, we can know for sure that the graph will look something like this. So we're going to sketch that down slowly. There's a delay in my software here. Please forgive me. Right. Now that is the first part of the graph. And then for any x value, that is less than 0, for any x value that is less than 0, you will notice that the y is actually less than 0. Therefore, the graph will only appear in this quadrant here. So therefore, I'm going to draw that. And then there you have it. That's the second part of the graph. right? And then the graph does not appear in any other quadrant other than this two quadrant. And then we can see the asymptote quite clearly, whereby the graph is approaching very closely, but it will never cross over. All right. All right, last but not least, as I mentioned before, we can determine the range for these functions if you have already draw out the graph itself. Since we have draw out the graph itself, and then since there's no stationary points, um, we will be able to determine the range for this function here. So the range for this function, I'm going to write it down here. The range is all right. Now it can be observed quite clearly from the graph itself. The range will be y are all real values except y equal to 0. So this is the range for these particular functions there, right? Now, other than that, just before I end this graph here, some of you might be wondering uh, how the shape of the graph would actually look like in more detail, right? You can also make use of the differentiations sections, even though it does not provide us with the stationary points, but we can make use of the dy dx just to identify or determine what sorts of gradient or functions that we are looking at. In this case, you will notice that the gradient is always negative. So therefore, the gradient or tangent of the graph is always negative for all the uh, real value of x. You can see that the gradient is going down. This gradient is also going down. So that is also another way to tell what sorts of shape does the graph take in this case, right? So I hope that will give you a complete picture of how the functions look like. All right, let's look at the second example of our rational function graph. Okay, now here we're going to sketch the curve that is given by this y equal to 1 over x minus 1. And we need to show all the points of intersection with the coordinate axis. And then lastly, we need to state equations or asymptotes. All right. Now again, I would like to remind you of the guidelines that we're going to use. Again, so number one, identify and determine any domain and range if possible in this case. Right. And then number two, identify or determine the intercepts of x and y axis. And then number three, identify any asymptotes, vertical, horizontal, or oblique asymptotes. And then lastly, identify any stationary points, may be local maximum, local minimum, or inflection points. So this is our second graph that we're going to sketch, right? We're going to go back to the drawing board. We're going to sketch this out. Stay tuned. All right, welcome back. This is our second example, where the numerator usually consists of a constant. The denominator usually has um, factors. It's either one factors or two factors in this case. But nevertheless, the degree of the numerator is always smaller than the degree of the denominator. So now we're going to follow the same guideline again. So in this case, the first one would be to identify any domain, any domain that you can identify in this case. All right. Now, since the question never mentioned um, any particular domain in this case, right? Not like the bicycle pump just now. For the bicycle pump, the volume usually should be greater than positive or more than 0 in this case, right? So for this, we are going to make a general assumptions here. We assume that x are all real numbers also. So x are all real numbers, and then of course except except x is equal to 1, right? It can take all the real numbers except equal to 1 there. Now this indirectly gives us an idea of the asymptote system, right? So there you have it. At this point we um, can't really figure out like the the range for this function. So maybe we're going to wait until the end after we sketch everything, then we can finalize the range itself, right? So second step or second guideline here, we're going to determine any x and y intercept. Okay. Now we will notice that um, there is no x intercept, okay, because y um, cannot be equal to 0, right? So therefore we don't have any x-intercept, but we do have y-intercept. For y-intercept, x is equal to 0, therefore y is equal to -1. Therefore this graph actually intercept the um, y-axis at -1, right? So that's the one. Okay, don't forget to label the axis also. I forgot that. Okay. Now, the third guideline would be the asymptote. So indirectly, we have already found the asymptote. So one of the asymptote, the vertical asymptotes, these are all asymptotes here. We are looking at vertical asymptote. Vertical asymptote would be x equal to 1. So this is the vertical asymptote, right? And then as usual for the horizontal asymptotes, as x approach positive or negative infinity, we notice that y would approach a 0. Therefore, the vertical asymptote, okay, y equals 0, is the sorry, it's not vertical, it's the horizontal asymptote, right? Okay, it's one of the horizontal asymptote. And then we are almost done. And then, of course, we need to follow through the last guideline to determine any stationary points. So from here, our dy dx would be basically 1 over x minus 1 squared. Right. Now you'll notice that the gradient of this graph is very similar to the previous graph. This is always less than 0. um, I would say less than 0 for all value of x except for x equal to 1 there, right? Okay, so it will be less than 0 for all value of x except x equal to 1 there. So I would say um, for all value of x, sorry about that, let me clean it up. For all value of x which are real numbers except 1. Okay, so that is the gradient of the graph itself is always negative. The gradient of the tangent is always negative for all value of real numbers, for all real numbers of uh, x value, except for x equal to 1 here. Right? Okay, now therefore, by looking at this first derivative, we notice that there is no stationary point that we can actually identify. Right? So therefore, we say that there is no stationary. So there's no stationary points. Therefore, we don't need to worry too much about the stationary point. Okay. Now from here, all we need to do is just identify if there is any intercept. So here we have a 0, -1. So the graph would sort of pass through here, -1. Okay, and then let me see any other. All right, now we have horizontal asymptote. The horizontal asymptote is still the same, which is this. So I'm going to draw a dotted line here. Of course, in the exam, you don't really need to do so because it's very hard to differentiate if you draw on the line itself, right? And then next we have a vertical asymptote. We have vertical asymptote at x equal to, this is -1, at x equal to 1 here. So this is 1. Okay, I'm going to draw that vertical asymptote. So this is x equal to 1. All right, now that is our vertical asymptote. So from here, we are going to sketch our graph. We know that the gradient is always negative, and then the shape does not differ too much from the previous example. Right? Now, we also notice that for x greater than 1. In this case, we're looking for x greater than 1. Therefore, we expect to see the y is always positive. So we know that the graph must actually exist over this side here. The same thing when x is less than a 1. We notice that the y is always less than 0. Now, that's how we know that the graph should look something like this. Right? So the first part of the graph definitely is going to come down here. All right, and there you have it, approaching. And then next, we also have the other part of the graph here. Yeah, it's going to pass through here and then going down and then going very close to the vertical asymptote. Right, now generally this is how the graph look like in this case. Right, now I hope that is clear. You can check the gradient is negative all the way. We have identified that the graph passing through this intercept here, and then there is no specific stationary points here, right? And then lastly, yes, before I forgot, I always forgot this. If you want to determine the range itself, so the range can be identified quite easily. So the y are all real numbers, okay, except equal to 0 here. Right. Now, of course, if you want to put into a real life context, then you have to check whether your domain can accept negative number or not, right? Okay, so I hope that is clear for this example. Stay tuned for the rest of the example. All right, this is our next example of rational functions. Let's take a look at this. Okay, the same instructions here. It's just that we are given different functions now. Our rational function is y equal to 1 over x minus 1 multiplied by x minus 2 here. So we have two factors, two linear factors at our denominator. So we're going to show all the points or intersections of this rational function and then state all its equations or the asymptotes. Now, don't forget, always remind yourself of the rules. How do you sketch the graph? I'm going to highlight the rules one more time, just as a reminder. Okay, so you have rule one, domain and range. Rule number two, guideline number two, x and y intercepts. Um, Guideline number three, identify any asymptotes. Number four, stationary points. Now, these are our next functions that we're going to sketch. All right, let's look at our next graph. Next, rational functions also satisfy the first criteria, where the degree of the numerator is smaller than the degree of the denominator. All right, now we're going to follow the same guideline here. Okay, so the first guideline would be um, to identify any domain. Okay, as usual, if the question never gives us any domain, we can assume that we can accept all real numbers. Okay, now of course, except 1 and 2. We can take all real numbers except 1 and 2, right? Now, secondly, we want to identify if there's any x and y intercept in this case. Now, we notice that there is no x-intercepts, but we do have y-intercept. So, for y-intercept, we will let x equal to 0, of course, right? So by letting x equal to 0, we indirectly got ourselves y equal to half here. So that will be our y-intercept at this particular point. Maybe you would like to write it down as a point, for instance, 0.5 here. Okay, and then we can actually mark it down on the axis there. So let me write down here. Um, is actually 0 and 0.5. Okay, so that will be somewhere here, for instance. Okay, all right. I hope that is clear. Right. And then our third guideline, we have to identify any asymptotes. So asymptotes usually is given when we highlight our domain in this case. So therefore, we can say that our vertical asymptotes are, in this case, we have the equations x equal to 1 and x equal to 2 here. Now, knowing that are our vertical asymptotes, therefore we can highlight it over here. So we're going to put it down here roughly. So this one will be our vertical asymptote number 1. This is x equal to 1, and then we have another vertical asymptote, which is, did I get it right? Yeah, x equal to 2. Okay, so those are our asymptotes here, x equal to 1 and x equal to 2 here, right? Okay, next we're going to go for our horizontal asymptote. Now you will notice that for all the example that we have attempted so far, where the numerator is smaller than the denominator, the horizontal asymptote is always, here I make it easier for some of you, the horizontal asymptote is always y equals 0. Okay, you can test it out using the same criteria that we did previously. Alright, okay, and then lastly, we're going to work out the stationary points here. Right now, to work out the stationary point, of course, you can differentiate it as usual, or you can revisit your partial fraction. So here I'm going to revisit the partial fractions again. We can do it this way. We can write this as a partial fraction. Okay, so you can say that this is actually a x minus 1, b x minus 2 here. All right. And then by solving this, okay, you will notice that now I'm going to write it down so that you can see what is going on. Equivalence to 1. Okay. All right. Now from here, you can substitute x equal to 1, for instance. Let x equal to 1. Therefore, your a would be equal to a negative 1. And then you can repeat the same procedure by letting your x equal to 2 here. Therefore, your b would be equal to a 1. Therefore, we can finalize our partial fractions for our rational functions as um, negative 1 over x minus 1 plus 1 over x minus 2. Okay, so I hope that is clear. Now I'm going to erase off the sections that I don't really need here. Okay, just that is just to recap, and then I'm going to finalize this directly without writing it too much. Okay, so this one can be written as negative 1, 1 over x minus 2 here. Okay, now the main reason why I want to write down as partial fractions is because it's easier to differentiate in this case. Alright, so we know that the y is actually equal to this dy dx. Now differentiating this will be a piece of cheesecake, right? Now that would actually give me x minus 1 square minus 1 over x minus 2 square. Okay, right. Now in this case, it's possible we can have um, some one or more stationary points here. We're going to equate this equal to a 0 there, just to see whether we can find any stationary points. So from here itself, you will find that we have what do we have here? We can say that the x. Okay, let me see. So in this case, we found that x minus 1 is actually equal to x minus 2 here. Do you think that's correct? Just wondering. All right. So from here, you found that if you solve this, you will find that there is no solutions here, which means there won't be any there won't be any stationary points. That's what I have found out, right? So just let me check one more time if I got it correct, right? So hold on. Mm, Let me see here. We have this. Just let me check for a while in case I make mistake here. We can have. Okay, just let me check properly. Instead of simplifying directly. So generally you have x square is equal to x square here. So if I were to simplify this, I'm going to write down at the side here. I will get a negative 2x plus a 1, and then that will be a negative 4x plus a 4 here. Therefore, I will get a 2x equal to a 3, and then therefore x will be equal to a 1.5 there. So indeed, yes. Indeed, in this case, we do have a stationary point at x equal to 1.5 here, right? So therefore, just a reminder, even though both sides are square root, some of you will be tempted to remove the square root, or remove the square in this case. Sorry, right? Remove the square, like what I did just now. Okay, if you're running out of time, you want to remove the square directly. Yes, you will lose a lot of information. You may find that there is no stationary point. But if you actually square them up, you found that yes, there is one stationary point that is located between x equal to 1.5 there. Okay, now you can find out this stationary point easily by substitute this x equal to 1.5 into here. All right. Now, before I'm going to continue any further, I'm going to mark down all the point that I have currently. So I have this one. So if I substitute x equal to 1.5 into here, uh, I will get a negative number. So just let me try this out roughly before I finalize the answer itself. So this one will be 0.5 by negative 0.5 here. So I'm actually getting negative 1 over 0.25 here. Okay, so therefore we have like a 4, a negative 4. X 1.5, and then a 4 at a negative 4. So most probably somewhere here then, if I want to make it more realistic. All right. So that's where my stationary point is located. Okay. Now, for at this point of time, you might be wondering what sorts of stationary points is this. Yeah. Okay. So if you don't want to proceed on with the second derivative, we can use an alternative way to determine um, the nature of this stationary point. Okay. Now to do that, I'm going to write at the side here to determine the nature. Okay, maybe I'm going to erase all the guideline first, so it's easier for us to follow here. Okay, let me clean this up so we don't need this guideline anymore. Okay, our dy dx. So I just keep our dy dx. I'm going to rewrite my dy dx again. Therefore, my dy dx is equal to 1 over x minus 1 square. Okay, that's my dy dx. And then I don't really need this anymore. Let me clean this up. Okay, don't need this anymore. And then I have already found out my stationary point. So my stationary point is found at this point Q here, for instance, which is 1.5 negative 4, which is here, 1.5 negative 4. This is our Q. Okay, now in order to determine the nature for this point, all I need to do is just get a line graph. Okay, just get a line graph here, and then this represent the x. I just need to put 1.5 here because 1.5 is the critical point. Now what I need to do now is um, to check for any value. Okay, now let me draw it properly. Hold on. I think I get a straight line better. Right, I'm going to draw a straight line here, and then after that I'm going to enter all my critical point. So I have my 1.5. I also have my asymptote here, which is a 2 and 1 here. So all I need to do is using trial and error, like in between 1.5 to 2, for instance. So I can try out, substitute any value in between here into my dy dx. Yeah, by the way, this part is x, but the value that I'm trying to gauge is the gradient of the tangent. So I can actually put in any value in between. So if I put it in, this is positive value, okay, for sure. And then this one would also be a positive value, okay. So therefore, whether it's going to give me a negative or positive, I'm going to find out. Okay, so take for instance, if I take 1.8, okay, 1.8. So if I put into 1.8, x equal to 1.8, my dy dx will be 1 over 1.8, so 0.8 square minus of 1.8, so 1.8 will be 0.2 square. Now you will notice that this number definitely is larger than this number here, so therefore it must be a negative. All right. And then I can also check out this number here, for instance, like 1.2, for instance. So what will be my dy dx? So if I put 1.2 inside here, I will get like 0.2 square minus 1.2. 1.2, I will get 0.8 square then. Therefore, you'll notice that this is bigger than this now. It must yield a positive number there. Actually, at this point, we can decide the nature of this stationary point. Now, we notice that this is a positive. Positive means going up. And then a stationary point is a zero gradient. And then when you see a negative, it means that the slope is coming down. Therefore, the shape itself give you an idea the types of stationary points that you're looking at. It must be a local maximum. Therefore, at this point, I can straight away sketch, since I know that both of these are asymptotes, so I can sketch straight away. And then, yep, and then there you have it. That's the first part. All right, now I hope that's clear. Okay, and then the next part would be we have already found the horizontal asymptotes. Yeah, the horizontal asymptotes is this part here. Right. The horizontal asymptote, just let me draw it out so that you can see it from here. We know that horizontal asymptote must be y equal to 0. Okay. And then you can also use a very simple rule, for instance, for x that is greater than 2, for instance, you can try. For x that is greater than 2, the y must be more than 0. Therefore, it gives us a direct idea of the graph actually um, appearing over here. And then bear in mind, since it appears here, right, the only shape that we can have is something like this. Yeah, we cannot have any other shape. And then the gradient is always negative. You can check for any x that is greater than 2. Greater than 2. So take for instance, if it's 3, for instance, if we put 3 inside, oh sorry, if we put 3 here, this number will be much more um, smaller than this one. So therefore, this one is negative. Therefore, the gradient is always going down. For x that is greater than 2, the gradient is always less than 0. Okay, right? And then next, for any x that is less than uh, less than less than 1, for instance. Okay, for any x that's less than 1. Okay, anything that is less than 1. Okay, now that must be a positive number. So you notice that the y is also more than 0. Okay, so and then it has to pass through this point here. Therefore, yeah, one more thing, if you are interested to know what is the gradient for this graph, you can always check out anything less than 1. Anything less than 1, you can put it down here. Take for instance 0, for instance. 0 is the easiest one. So if I put 0 here, you'll notice that it's a positive. It's a positive gradient. So positive gradient, yep, that actually fulfill very nicely our graph in this case. This one going up all the way here. And then there you have it. That is the graph for our rational functions. All right, now before we end, I almost forgot. Now, for some of you who are interested in the range itself, you will notice that this graph would never exist in between anything in between -4, 0 and -4. So the graph will only exist for the range itself, the last part. For the range, the y must be greater than 0, uh, or y must be less than or equal to -4. So the graph only exists within this range here. All right, so I hope that is clear. Right, now we have look at functions, rational functions, where the numerators consist of constant. Now we're going to look at another format of rational functions where the numerator consists of linear functions, whereby its denominator is a quadratic functions. Or in general, we can say that the degree for the numerator is 1 smaller than the degree for the denominator. Right. This is a very real life example that I have found um, and applications that has been used in medical industry. So you can look at this example here. After taking a certain antibiotic, the concentration of this antibiotic in the patient's bloodstream is provided by this mathematical model, CT, where the C stands for the concentration, the T will be the time where the drug has already entered into the bloodstream. All right. So we're going to look at how does this graph look like as compared to the previous graphs that we have sketched so far. Now again, I would like to walk you back to the guidelines. So we have the first guideline, domain and range. Second one, the intercepts of x and y axis. Next, asymptotes. And then lastly, stationary points. Now this is the functions that we're going to sketch this time. Instead of having x and y, we're going to be more versatile in the way how we represent our functions and graph. All right, here is our next graph that we're going to sketch, which is a rational function, but this time we are given in the form of T. C stands for the concentration of the antibiotic after it has entered into our bloodstream. Okay, now we're going to follow the same guidelines here. So the first one will be, all right, first one will be here. We're going to write down the first one. We're going to find out any domain here. Now, of course, based on these questions, uh, t represent the time itself. So the time should be anything greater than or equal to 0, right? But for the knowledge and skill of sketching the graph itself, I'm going to use that domain where t are all real numbers. So here I'm going to make a general assumptions here. The t are all real numbers. Of course, except t is equal to plus or minus 2. So that are the only two values where the concentration of the antibiotic is unknown. Right? Other than that, for all the real numbers of t, yes, we are able to determine the concentration of the antibiotic. Okay, so I hope that is clear at this point. Yeah. Now that also indirectly give us the vertical asymptote. So I hope that you still remember this part. Instead of labeling as x, we have to label that as t now, and then whereby this is concentration here, because we have a 0 here. All right. And then now we have done with number 1. Maybe we can go directly to number 2. Our number 2 would be find out any x or y intercepts. In this case, is very direct. We notice that ct is equal to 0 at t equal to 0. So therefore, that actually gives us the indirectly is a x and y intercept, or in this case, is a t and ct intercept. All right. I hope that's clear at this point. All right. Generally, that is the only intercepts for the axis, yeah, that we have, right? And then number 3, we have found the vertical asymptote. So here I'm going to write it down, vertical asymptote. So vertical asymptotes are x equal to -2 and x equal to +2. So therefore we have one positive, one negative here. So roughly, I'm going to draw something like this, -2. So maybe this one is a 2, for instance. So I'm going to label this vertical asymptote. Just a rough sketch. So x equal to -2, and then we have x equal to 2. All right, now there you have it. Oops, I'm using the wrong symbol here. Just let me correct that. Instead of using x, I think I get used to x most of the time. This is t itself. Okay, now we are good. All right, and then next, we are still on the first case where the degree of the numerator is smaller than the degree of the denominator. Right? Therefore, the horizontal asymptote must be y equals 0, or in this case is ct equal to 0. Okay. Now, how do we actually work it out if you are not sure which case that you are looking at? We can always say that Ct is given by 0.04t, t squared minus 4 here. You can divide the numerator and denominator by t squared. So therefore we have 0.04 t, and then that is a 1, 4 divided by t squared. Alright, now as t approaches positive or negative infinity, we notice that this approaches 0, this also approaches 0. Therefore, the whole concentration functions will approach 0 there. That's how we know that the horizontal asymptote is. Okay, so here we can write down the horizontal asymptote as Ct equal to 0. And then there you have it, right? So this is the simple way of determining the horizontal asymptote. But anyway, you can always take the shortcut, knowing that the numerator has a degree smaller than the degree of the denominator. Then you can straight away write down the horizontal asymptote is equal to 0. Okay, so we don't need this anymore. Let me, oops, we need this. Never mind. Just let me rewrite that again. So here we have vertical asymptote as x equal to plus or minus 2 there, right? And then the horizontal asymptote, shouldn't write x, I should have written down t equal to plus or minus 2, right? Horizontal asymptote will be ct equal to 0 in this case. All right, now I hope that's clear at this point. Okay, now our next guideline will be to determine its stationary points. All right, now the same thing here, we are going to work out its partial fraction so that it's easier for us to differentiate, I would say. So we can actually let Ct equal to this is the partial fraction, and then from here we will have equal to Ct. All right, now Ct is actually equal to this, so I can actually write it down as this one here, which is the same as okay. Now, of course, you can substitute any value. For instance, substitute t equal to negative 2, for instance. Therefore, we have negative 4a here. Is it negative 4a? Yeah, correct. Negative 4a. And then you have your 0.04, negative 2 here. Okay. And then, therefore, your a will be 0.02 then. Okay. And then do the same thing for t equal to 2. So if you substitute 2, then your b indirectly will be also 0.02. All right. So therefore, both your a and b are 0.02. Okay. So just let me clean this up. We will have 0.02. The other one also 0.02. Okay. There you have it. That is our partial fractions. So we don't need this anymore. Okay, now we are ready to obtain its derivative. So from here, we can get c prime. Okay, we're going to differentiate this with respect to t. Now we will get, I can actually factorize everything. So, or I can leave it as 0.02 t plus 2 square. Here, right? Now the same thing, we are going to equate this equal to 0 in order to locate the stationary point if we have any. So from here, we will get 0.02 t minus 2 here is equal to 0.02 t plus 2. Okay, so from here we have t squared minus 2t plus a 4, t squared plus 4t plus a 4. All right, that's what we have. And then from here, let me see what we have here. So from here, we will have 2t squared. Okay, if I'm not mistaken, it's 2t squared. And then after that, I will have like a 2t. Okay, and then lastly, I have 8. So that is basically t squared plus t plus a 4 here, equal to a 0 there. Now, therefore, at this point, we expect to have two stationary points, sort of. So you might be wondering whether we have a solutions for t or not sometime. Okay, as I see it from this point of view, I may thought that there is a solution. But you can always check your b squared minus 4ac at this point. Okay, all right. So if you check your b squared minus 4ac, you will notice that the discriminant is less than 0. So therefore, there is no real solutions to t there. Because there's no real solutions to t here, therefore, there is no stationary point. So here we can conclude that no solutions here, no stationary point. All right, now for those students who are interested to work out as to why, give it a try. If you still can't get it, drop a message on my channel, then we can discuss more, right? All right, now there you have it. Okay, no stationary point. And then the other thing we are interested to find out is, even though there is no stationary point, but is there any inflection point, just in case? Okay, so inflection point might be new to some of you. Inflection point can be located by allowing your second derivative equate equal to 0. So now I'm going to differentiate this one more time. Okay, so that would actually give me like 0.04 t plus 2 cube, and then the same thing here, 0.04 cube equal to 0 here. All right. So from here itself, I would be able to sort of get like t minus 2 cube plus t minus 2 t plus 2 cube equal to 0. All right. Now let's see whether we have solutions to this. Okay. Now of course you can actually expand everything here, and then you should be able to obtain a solutions here. All right. So one of the solutions would be, I think for me the easiest way would be here. You can actually write it down as let me see here, what do we have? Do here. Yes, you will be able to find out that t is actually equal to 0. Okay. Now maybe I can work it out here. All right. Okay, I'm going to keep it up to this point here, and then I'm going to write it down at the side here so that you can refer. I don't have much space left here, so I'm going to write it down here. The shortest way we can do this is, if you don't want to expand that, you can actually write something like this. Okay, all right, now this is 3. And then from here itself is the same as t minus 2 cube is equal to negative t negative 2 cube. Because if you factorize it out, it's actually a negative, right? From here, we notice that both sides are cube. So therefore, we can actually equate this here. So therefore, you found that your t is actually equal to 0. Now, from here, we found that there is an inflection point at t equals 0. If you substitute t equals 0, you found that your ct value is actually equal to 0. Therefore, the inflection point is actually located at the x and y intercept. Okay. Now, of course, this part I leave it up for argument. All right. Anyone would like to expand it, or if you have um, any formula for cubic for factorization, you can always use it, right? Now, for the purpose of the sketching of graph, here I would leave out these sections. You can always drop your questions on my channel there, right? Okay, so we have an inflection point here. All right. Okay, now basically we are almost done at this point. We are ready to sketch. Okay, now let me clean up the thing that we don't really need here. So for instance, this part we don't really need. Okay, now we are ready to sketch. So the first thing would be, as usual, for t that is greater than a 2, for instance, for t that is greater than 2, you will expect, yeah, let me write down, for t that is greater than 2, you expect the ct must be greater than 0. So therefore, the graph must actually appear this part here. Alright, so let me draw it out here. Alright, now that's the first part of your graph. And then you can always test out the second part for t that is less than negative 2, for instance. For t that is less than negative 2, you will notice that this denominator is always positive, but your numerator is a negative. So therefore, ct is less than 0. It's less than 0. So therefore, anything less than this, the shape would look something like this. Alright, now that's the second part of it. Okay. Now, the part where is pretty challenging will be here. Right? Will the graph be because you need to pass through here, so therefore it's either this shape or this shape here. So how do we decide? Okay, we're going to look at the gradient itself. You'll notice that the gradient is always negative. This is always less than 0 because it's negative, less than 0. So therefore, the gradient is always going down instead of going up. Therefore, we can conclude that the shape of the graph would look something like this. I need to be more precise at this point. This part is the inflection point, and then going down here. Yep, and then there you have it. I did not draw this properly at the end here because this tail is supposed to get closer and closer to the asymptote. All right, and then there you have it. This is our graph for these concentrations of antibiotic. Right, but for the range itself, lastly for the range, you can see that it can accept all real numbers. Okay, it can accept all real numbers here, right? But for the real applications purpose, the correct domain usually would be, in this case, the time must be greater than or equal to 0, as you can see, right? And then concentration, usually we don't have negative concentration here. Therefore, the range itself, for realistic approach, the range itself, the concentration is always greater than a 0 here. It would approach pretty much very near to 0. because the antibiotic has already take effect in your body itself. So the amount will slowly reduce. But I would say there will be a very tiny small particle that's still left behind. Right? Okay. So I hope that is clear at this point. We have already applied all the four guidelines there. Right? Okay, stay tuned for the next graph. Right, just to give you more practice on this form of rational functions, I have already selected one more example of a functions that looks quite close to the concentrations or antibiotic example. So here you are given the curve y is equal to x over x plus 1 and then x minus 3, right? It also fulfill the main requirement. The degree of the numerator is one smaller than the degree of the denominator. All right. Here we need to determine all the points of intersections with the coordinate axis. We need to find all its asymptotes and then determine any turning points if possible. And then lastly, once we satisfy with all the properties, we're going to sketch the graph. Right? Now, guideline again. Same thing. I'm going to keep on reminding you of the guideline. First one, uh, determine any domain or range, right? And then x and y intercept, asymptotes, next stationary points. And then this is the graph that we're going to sketch shortly. Right, here is our next graph where the order of the numerator is still smaller than the order of the denominator. All right. Now we're going to follow the same guideline again. Okay, so from here we will have domain. Okay, now it's not stated here, so we're going to accept all real number of x, except of course -1 and 3. Now this one will be the domain for this rational function, right? And then indirectly we have found out the vertical asymptote, right? Now number two, we're going to find out any x and y intercept. So it's pretty obvious for x and y intercept. For y intercept, you will let your x equal to 0. So if you let your x equal to 0, your y indirectly is a 0. Okay, and then for your x-intercept, we will let our y equal to 0 there. So if you let your y equal to 0, then therefore your x is also equal to indirectly is 0. So therefore, uh, the graph actually passes through the origin. All right, I hope that's clear. This is y, is x here, and then it passes through the origin. Okay, now our third guideline will be asymptotes. We have already found its vertical asymptote here. Okay, so vertical asymptote is x equal to -1 and x equal to 3. So we have two vertical asymptotes. One is at -1. So I'm going to sketch that out. Okay, that's the first one. And then the second one is at 3. 1, 2, 3, roughly, somewhere here. 3. All right. And then I pass through there. All right. Okay. And then as usual, we also found that the horizontal asymptote for these conditions, the y is always equal to a 0 there. So which means this is also one of its asymptotes. Okay, and then there you have it. All right, at this point. All right. And then next, guideline number 4 are the stationary points. Okay. As usual, we're going to form the partial fraction for this so that it's easier for us to differentiate. Okay, so therefore, in this case, we can write you can write its partial fraction format. Okay, and then there you have it. Now the same thing, you're going to allow your x equal to -1, for instance. Um, so -1 here, you will get a equal to, so that is a -4 here, so that will be 1 over 4 then. And then the same thing, you're going to let your x equal to a 3. So if you let your x equal to a 3, and then your b would be, this one will be a 3, so that will be a 3 over 4 there, right? So indirectly, we have our partial fraction form. Okay, now I'm going to erase off. We don't really need this anymore. I just want to rewrite this partial fraction form correctly. So the A is a quarter, and then the B is 3/4. Okay, and then there you have it. All right, now of course for the differentiation, I just wrote it down wrongly. Hold on. Square. Now again, you'll notice that the gradient of this rational function is always negative because this gradient is always less than 0. Okay, so you expect the graph is always going down in this case. All right. So therefore, let's see whether we have any stationary points or not. So from here itself, we will have, let me see here. This is 1 over 4, 3 over 4. So that will be, um, let me see, x minus 3 square negative, which is equal to a 3. Is it 3? Yeah, correct. 3x plus 1 square here. Alright, so that's how it actually look like. In this case, it would be quite obvious if you want to check. Generally, there is no stationary point. It's either you expand it and then use the discriminant to identify whether there's any um, solutions to this or not. Right? Now I'm going to show you both. Okay, I'm going to erase off all this. We don't need this anymore since we have already identified that. Okay, now you can see that our dy dx, when we let our dy dx equal to 0, so our dy dx is actually equal to negative 0.25. Let me rewrite that again. We know that this gradient of tangent is always less than 0. Okay, and then we reach this conclusion when we want to determine its stationary point. So we have a negative x minus 3 square is equal to 3x plus 1 square. Now you can solve it simply by taking square root both side. Yeah, you notice that by taking square root both side, it will yield a complex number. So therefore, there is no real solution. No real solutions here, right? Or secondly, we can expand everything. Okay, we can expand everything. So let's try to expand that. Okay, so if you expand that, you'll get. All right, we'll get this. And then if we try to simplify everything, you get 4x squared. And then the 6 is gone. So you can see that the 6 is gone. And then after that, we will have like a 12. All right, equals 0. For any real solutions, we know that 4x squared plus 12 must be greater than 0. So therefore, there's no real solutions. Or you can say that um, basically x are all complex number, I would say. Okay, so that's the thing. No real solutions, so it means no stationary point. All right, now I hope that's clear. All right. Then again, you might be wondering, is there any like inflection points on it? Yep. It's always good for us to check that out. So if you get the second derivative, so second derivative here will be 0.5, and then that one also the same, 1.5. Okay, you can equate them equal to 0. Okay, so from here we will have let me see. So that is a 3 x plus 1 3 equal to a negative x minus 3 3 here. All right. Now you can apply the same strategy like what we did. Um, yeah, but this one will be a little bit tougher because there's a tree here. Just let me see whether I got it right or wrong just now. Okay, mm, tree. Yep, that is correct. Right. So from here, um, we can try to solve this. Okay, so if you try to solve this, you will get like let us give it a try. So that is actually 3x plus 1 3 minus x. If we bring the negative inside there. All right. So this is how it look like. And then from here itself, we can write down is equal to root cube root 3 cube root 3 and then x plus 1 here. All right. So from here itself, we should be able to obtain inflection point, an inflection point, sorry. All right. So that is actually 1 plus root 3. 1 plus root 3, let me see, is x. And then thereafter we have 3 minus root 3. Okay, and then there you have it. We do have an inflection point, and then this inflection point is a positive number. The number I leave it out for you to figure that out. But we do know that x should be a positive number in this case. That will be somewhere here. Yeah, somewhere here. And then for that, you can find out the y value. All right. So just let me give it a try. Let me see what do we have here. So that is like let me see, 3 to the power of okay. So that is 1.44 approximately there. So that is 1.56 there. Okay, hold on. 1.56 So 1.56 divided by, let me try, by, okay, it's approximately 0.60. I'm just making an assumption 0.6 should be around here. So if I put 0.6 somewhere here, I will get a negative number. So most probably the inflection point will be somewhere very close here. Yep, there's the inflection point. So there is an inflection point. You also pass through the x and y intercept there. All right, and then now we are ready to sketch. We know that the gradient are all negative. Okay. Now for the first test here, for any x that is greater than 3, for any x that is greater than 3, then we found that the y is always greater than 0. So therefore, the first part of the graph would definitely be this section. Yep. Okay. And then for the graph in between, we know that the gradient is negative, and then it passed through here. So the only way to sketch this is over here. You need to pass through here generally, and then there's a sort of an inflection point, and then after that going down here. All right. And then lastly, for any x that is less than -1, for instance, anything less than -1, the denominator is positive, but the numerator is negative. So therefore, y must be less than 0. Therefore, it will look something like this in this case. All right, and then there you have it. That's the graph for this function here. Of course, you can identify the range very clearly in this case, right? So stay tuned for the next function. Okay, now next I'm going to present to you another form of rational functions where its degree for the numerator is equal to or or bigger than the degree for the denominator. So if you have these types of rational function where the degree of the numerator is equal to or greater than the degree of the denominator, then we are going to follow the rules to sketch for these sorts of rational functions, right? Now I'm going to walk you through the guidelines again, the same guidelines we're going to use, but there will be more features to explore for these types of improper rational functions. All right, this is improper rational functions. So same thing, we get to figure out determine the domain and range, um, identify any intercepts, next asymptotes, and then lastly stationary points. And then this is the graph that we're going to sketch shortly. All right, this is our next rational function, which satisfy the second conditions where the degree of the numerator is equal or smaller than the degree of the denominator. Now for that, usually I call this improper rational functions. Now, bear in mind, in order to perform improper rational functions correctly, you have to properly, you have to turn these improper fractions into a proper fraction. That's the reason why you have to perform this properly, right? So turn it into a proper fraction. That's the key idea here, right? So whenever you found that this is improper fraction, we're going to convert it into a proper fractions by using long polynomial division. Okay, it's not really that long. Okay, so the first step is to perform the long polynomial divisions. All right, now we're going to do that in a while. I'm going to go through the guideline again. So the first one, we're going to assume that the domain are all real numbers, of course, except x equal to -2. Yep, all right. And then next, any x and y intercept. Yeah, that is very obvious in this case. You get your y-intercept. So your y-intercept in this case is y equal to 1.5, and then your x-intercept, I should put a s here just in case. So x-intercept, for x-intercept you let your y equal to 0. So therefore we have x equal to -3. Okay, we're almost there. Number 3, our vertical asymptote. Vertical asymptote. In this case, it's very obvious. We only have one, which is x equal to -2. And then our horizontal asymptote. This is the part where we need to perform the long polynomial divisions. Right. So by performing the long polynomial division, I'm going to do it at the side here, just to recap the procedure again. That is very obvious. You get a 1 there. Therefore, we can write this function as, all right, now there you have it. That will be the proper rational functions after we perform the long polynomial division. Right? So once you have that, it'll be easier. Okay. Now, from here itself, right, you can straight away write down the horizontal asymptote is basically these sections here. So the horizontal, sorry, not vertical. The horizontal asymptote is y equal to a 1 here. All right. Now the reasoning behind this is the same as x approach positive or negative infinity. What happened to this would be, we know that 1 over x plus 2 will approach 0. Because this approaches 0, therefore your y approach a 1. Then we make a conclusion saying that the horizontal asymptote is y equal to 1. Or in the exam itself, you don't really need to write this testing condition. You can identify the horizontal asymptote directly from this proper uh, rational function structure. Okay, so once we have done that, we're going to put in our label now. We have our vertical asymptote at x equal to -2. So -2 here. I'm going to label that. Dotted lines, don't forget. So x equal to -2. Um, let me see what else. There's a x-intercept, -3 somewhere here. All right, and then there's a y, oh sorry, x-intercept -3 here. Sorry, I put down the wrong one. And then the y-intercept at 1.5. So 1.5 most probably will be here. And then it's x and y. Okay, we are almost there. Just let me mark down the point here. It passed through here. And then next we have horizontal asymptote at y equal to 1. Okay, so y equal to 1. I'm going to do that. Oops. Just give me a while here. Let me clean up the... Okay, so it's supposed to be here. I should have drawn this further up, but it's okay. So this is y equal to a 1. Alright, now there's your horizontal asymptote. You have your vertical asymptote. And then generally we are almost there. Now we are almost there. So the last part is you are interested to find out if we have any stationary point or points or not, right? So we get to perform the differentiation. You'll notice that if you differentiate this, you only get x plus 2 square here, which means there is no stationary point. It's very obvious, no stationary point here. And then you are interested to find out if there is any um, sort of like inflection point. If you differentiate this one more time, you will not be able to get any inflection point here, right? So that one I leave it to you to work it out. Just let me put it up further a bit. It is not drawn to scale, just to let you know here. Okay, so it's somewhere here. All right, I think we are almost done. Okay, and then you also notice that the gradient of tangent is always less than 0, which means it's always going down. Okay, and then lastly, we just need to test the final criteria for any x that is greater than -2, greater than -2, then that must be a positive number. So therefore, the y must be positive. It means that the graph must appear here. So just let me try to draw this. Pass through here. Yeah, and then there you have it. That's the first part. And then the same thing go for x less than -2. Anything less than -2 here, it will be a negative. So therefore, it's supposed to pass through here. So therefore, it's going to go down, go very close there. And then there you have it. That is our rational functions for improper fraction. All right. And then for the range itself, I think you will be able to figure that out. Is all real numbers except for y equal to 1. So I just write it down for reference. Range. Here, y are all real numbers except 1. Okay. Stay tuned for the last example. Right, again, I have prepared for you another example which look very closely to the improper rational functions that we have worked with in our first example. Right, now this is the second example of improper rational function. Here they highlight that specific requirements that we are supposed to fulfill here. We need to find its asymptotes, number of determine number of turning points, and then finally we can sketch the graph. Right, now again, the guidelines. So firstly, domain and range, if we can identify them, the x and y intercepts, and then next you would expect very much the asymptotes, and then lastly stationary points. And this is the graph that we're going to sketch shortly. Right, here come our last example for this rational function. Okay, all right. Now we're going to follow the same routine again. We will say that our domain are all real numbers, of course, except x equal to -3 and 1. Okay, so there you have it. And then number 2, we're going to find any x and or y intercept. Is also very obvious here. Okay, we know that our y-intercept will be x equal to plus or minus square root of 5. Okay, and then our x-intercept so our x-intercept will be quite easy in this case. So x-intercept, we just let everything equal to 0. We will have 5/3. Okay, and there you have it. The x and y intercept. So let's mark it down. This is 2 point something. So 1, 2 most probably will be here. -5, 1, 2. roughly I would say set 5 over here. Okay, and then like 1 point something. Motion is bigger. This is 1.6 something. This is 2 point something. So 1.6 something will be somewhere here, for instance. All right, and then it passes through here, here, and here. That's the thing, right? And then number 3, we're going to find out all the asymptotes. Okay, here we have, I just write down the answer without writing the name anymore. This is x equals 3 and 1. These are the vertical asymptote. For the horizontal asymptotes, as usual, because we notice that this is an improper fraction, we must convert it into a proper fraction. Therefore, I'm going to perform a long polynomial division. Now, for long polynomial divisions, you will notice that there is no x. So it's better to write down x squared minus 0x minus a 5 here. And then we're going to expand the denominator, of course. All right, if you expand the denominator, you will get x squared plus 2x minus a 3. Okay, so I hope that's clear. And then from here, we can perform the long polynomial division. That is only a 1. So from here itself, you will have a negative 2x, negative 2 also. And then you will notice that the degree here is lower than the degree for the denominator. So therefore, we're going to stop our division, and then we are going to write down our y. So y can be written as 1 minus 2x plus 1. Did I get it correct? Let me see. Minus 2. This is 2x, so it's 0 minus, yeah, correct. And then divided by x minus 1, x minus 3. Alright, and then there you have it. As usual, after we obtain this, we found that the horizontal asymptote is y equal to a 1 here. Alright, so y equal to 1. Alright, now I hope that is clear at this point. Okay, I'm going to erase all this. I think I'm going to erase all this so that it's easier for us. Okay, alright. And then I'm going to label all my asymptotes. So negative 3 will be around here. I think negative 3 will be around here. Negative 3. And then the other one is a 1. So 1 will be around here, for instance. And then we have the horizontal asymptotes also. So maybe I'm going to draw this horizontal asymptote. Y equal to 1. So this part here is 5 over 3. This is a 1. And then I have my vertical asymptote here. Then I have another vertical asymptote. Okay, and then I'm almost done. Just let me check through all the points that it passes through. It passes through here, this point, this point. All right. So generally we are almost done here. Okay. And then lastly, we just need to find out if there is um, any stationary points in this case, right? Okay, but I think it's quite obvious at this point. Okay, right. Now I think I label all these color correctly so that you can identify them. This is negative 5. This is 5 here, and then that is 5 over 3. Okay, we are almost done here. Okay, then the next part would be we can actually perform the partial fraction so that we can perform the differentiations more easily in this case. Okay, I'm going to try this out. Number 4 here. Okay, so we have now the partial fractions that I'm going to work with will be this partial fraction here, this section. Alright, so I'm going to just consider this section here. Just consider this section. Now, therefore, we have. Let me write it down. So I'm going to consider. In this case, the y is actually equal to 2x plus 1, x minus 1, x plus 3. Sorry, 1 minus. Yep, I think I missed it out. Hold on, just let me clean it up. There's actually y equal to 1 minus. Okay, now I'm just going to consider this x plus 1 over x minus 1, x plus 3. Right, now that is equivalence to a over x minus 1 plus 3 here. Right. So from here itself, I will get 3 plus b x minus 1 equal to 2x plus 2. Alright, so I can let my x equal to 1, for instance. So if I let my x equal to 1, I have 4a here. That is a 4a must be equal to 1. Okay, and then I can let my x equal to negative 3. So negative 4b. In this case, is negative 4 also. So b is equal to 1. So this is 1 also. Okay, we are ready. I'm going to erase all this. I'm just going to put back all this partial fraction properly. Hold on. Because they are all 1. So this is 1, this is 1. Okay. Right. Now for that, our y is equal to 1 minus 1 over x minus 1 minus 1 over x plus 3. Okay. Now our first derivative will be 1 over x minus 1 square and then plus 1 over x plus 3 square. Okay. And then from here, you will notice that there is no solutions to that. Therefore, there is no stationary points. Okay. And then from the second part, okay, we will find that there will be, I think there will be a inflection point. Just let me check for a while if I got it. Let me see. Yes, a negative there. Oh yeah, there is no inflection points also. All right. I think there's no inflection point. Did I get it right? If I were to get the second derivative, okay, I'm going to rewrite this just to check properly. So my second derivative, that will be a negative 2x minus 1, 3 minus 2x plus 3, 3. All right. So from here itself, I will have x plus 3 cubed is equal to 1 minus x cubed. Okay, so if you equate everything, we found that that will be x plus 3, 1 minus x. So 2x is equal to negative 2, x is equal to negative 1. Alright, indeed there is an inflection point at x equal to negative 1. So at x equal to negative 1 here, we can put it back here. We will get, let me see what do we have here. We have negative 1, that is negative 2, 1 over 2, 3 over 2, and then this is 1 over 2, 3 over 2, 1 over 2, that is a 1. Okay, so there's a 1, so y is equal to 1. Okay, x equal to negative 1, this is negative 2 point something. And then negative 1, y is a 1, so somewhere here. Okay, so it fit in very nicely. Right, I think we are almost done at this point. And then you will also notice one thing about the gradient of tangent. This is always greater than 0. Therefore, the gradient of tangent is always going up. Okay, and then that can be seen directly from here. Right. Okay, I'm going to pause here. There's a lot of works to be done here at this point. Okay, once we have done that, now I'm going to erase off these sections that we don't really need. Okay, this is the part that we don't really need. Alright, and then we are ready to sketch the graph from here. The gradient is always positive, so therefore it must be going up here. And then passing through, and then going very near to the end. Alright, so that's the first part. And then the second part will be the gradient, because you need to pass through here. Gradient is positive. So therefore, I believe that the graph must look something like this. Alright, now that's the second part. And then, of course, you're wondering what happened to x that is less than negative 3. Okay, x less than negative 3. Alright, now we can give it a try for x less than, did I get anything wrong here? This is, yep, correct. So for x less than negative 3, we will have a negative number here, positive number, and then everything will be positive. So therefore, for x less than negative 3, y will be positive. So therefore, the graph would basically be up here. Alright, and then there you have it. That is the graph for these improper fractions. Okay, I hope that is clear at this point. Alright, now we still have one more sections where we're going to deal with what we call as the oblique asymptotes. Alright, now that one I will leave it to the second sections where we need to spend more times on that. Alright, so I hope that you can take this time to walk through the first part of this rational function, make yourself comfortable with all the analysis involved in the property of the graph itself, right? Okay, so until I see you again, enjoy math like how you like to enjoy a piece of cheesecake, right?